So now let's look at a soft lithography. First, so what is soft lithography? So why is it called soft lithography? The soft means there is no energetic particles like electrons or ions or radiation like UV or X-ray light. Just that we use the soft electrometric mode. So this mode is made of the PDMS. So the main advantage for the soft lithography is the low cost. So we do molding, printing, or transferring. So this printing is similar to the nano print. So that's why sometimes people call nano print lithography also as a soft lithography method. Usually the resolution is not very high because we use the PDMS. So PDMS is too soft for the high resolution. So the main application is in the microfluidics and biomedical areas. So the term soft lithography comes from the professor George Whiteside. So he's a professor from Harvard University. At one conference more than 10 years ago, it's called the Micro and Nano Engineering, the Micro and Nano Engineering Conference. So in the conference, everybody talk about how small they can make. So this professor here, so he said, size is not the only thing that matters. The function is more important. Because he made so many different, so his group developed so many different soft lithography methods, so they have more functions. That's why he have this comment. So the key material for soft lithography is the PDMS. It's polydimethyl siloxane. So this is the chemical structure of the PDMS. So why we use this material? So this is the most people, I would say 90% people, they use this PDMS. This from the Dow Corning. It's called the Silver 184. So actually, this PDMS is not used for the research. So this one is used to like a silicon sealant for the solar cell. For the solar panel, you want to seal it against the leakage of the water. This is used for that purpose. But researchers found that this material is very good for the to make the soft lithography. So they use this solar panel material, the sealant material, for the soft lithography. As we know, it is a silicon elastomer with different qualities. It is very flexible with low Young's modulus. It's only 1 megapascal. Typical polymer like a PLMA is several gigapascal. For the case of the silicon Young's modulus is 100 gigapascal. So because it is flexible, it conforms to different surfaces, conforms to the curved surface. It's chemically inert and optically transparent. So it is inert because it is cross-linked. So this material is cross-linked. It's transparent, as you can see this green color here. So this one is the PDMS. It's even more transparent than the sodium lime glass and glass lead. Because this glass lead and sodium lime glass, so they have metal dopant. This one has sodium. This one also have some metals, alkaline metals. But this one is no metal, so it's more transparent. So it has low surface energy because this methyl group, this hydrocarbon, not polar. This gives you the low surface energy. It can be bonded to the flat and clean surfaces for the microfluidic applications. So the bonding can be a permanent bonding or reversible bonding. Reversible bonding means temporary bonding. So that means it's bonded, you can detach it by a force. It is durable, reusable, and low surface energy. It is biocompatible. So now let's look at how to modify the surface energy. So when we look at this structure here, so because the air has no surface energy. So to lower the surface energy, this group here, the methyl group will be exposed to the air. If this one is exposed to air, so it will be like a kind of low surface energy hydrophobic. It is low surface energy hydrophobic. How to make it hydrophilic? So the easy way to make it hydrophilic is to do oxygen plasma treatment. So we have oxygen plasma. This one will burn away. It forms the hydroxyl group. So we have lots of hydroxyl group. It is hydrophilic. So when it becomes hydrophilic, you can do more things to do the bonding. So you have this surface, you have this hydroxyl group. Another surface, you also have this hydroxyl group. But then they can come together. So then when you bring them together and heat it up at like 80 degrees for a few hours, then this one will come together to form the water. So you end up with this chemical bond, as you see here. So you have the silicon-oxygen silicon bond. This is the bonding. If the temperature and the time is very high, you get irreversible bonding. That means a permanent bonding. If the temperature and the time is not so much, you have the reversible bonding or temporary bonding. So the problem is that, so even though you can make it a hydrophilic, but because the PDMS is the molecule is kind of movable, after about 10 minutes, so the methyl group below the surface will come over. So the top surface will become methyl group again. Because this one is low surface energy, stable state, high surface energy. This is not stable state. Only 10 minutes it will become like this. So as a result, this material is usually only good for the research. So most of the research for the microfluidics is done using the PDMS. But for the commercial product, this is not very good because you cannot maintain the hydrophilic surface. You need this oxygen polymer treatment. So this is not the unstable surface is not good for the commercial application. But this is one is very good for the research. So how to modify the surface? How to further modify the surface energy? So you can do this one. So first, you do the oxygen polymer treatment. When you do the oxygen polymer treatment, it will become the surface because you have a lot of silicon here. So the surface will become like a silicon oxide, and terminated by this hydroxide group. When we have this hydroxide group, you can treat it with the trichlorosilane to form this kind of self-assembled monolayer. But this X here determines the property of the surface. For example, if you want to make it hydrophobic, then this X will be something like this. So if you have a lot of fluorocarbon, then this one will be low surface energy. It will be hydrophobic. And this is the same thing as we have learned for the mode release agent for the non-imprinted lithography. So it is here. You can see this one is also a trichlorosilane. When we have trichlorosilane, it will bond to the hydroxyl group on the surface. So there is the same thing. We can modify the surface using this trichlorosilane to have different surface group. So one important property for the PDMS is that it is permeable to the solvent and to gases. For instance, if you put the PDMS, you put it in the solvent PGMEA. So this is the PGMEA. This is a very popular solvent for the resist. Then 27% of the solvent, you know that the weight, the PDMS can absorb 27% of its weight, and 30% of the PGMEA, this is the PGMEA, will diffuse into the air in about 1 hour. Now here is the permeability to air, to different gases, helium, nitrogen, and oxygen. As you can see here, the PDMS is this number here is much higher than the number for the polystyrene and the PMA. Now here is the permeability. So what is the permeability? So the unit of the permeability is a barrel. This is the unit for the permeability. So the driving force for this diffusion is the pressure gradient. So this is the unit. For the barrel. I will show you again. So this one is the unit for the barrel. You can see it is the cubic centimeter STP. STP means standard temperature and pressure. Cubic centimeter. So this is the amount of the gas molecule per area, per centimeter square, or per second, and per pressure gradient. So this centimeter mercury is the pressure. If you put this centimeter below the CMCD, it becomes the pressure gradient. So the driving force for this permeability is the pressure gradient. That means CCMG, CMHG over CM. That is the pressure gradient. But this is used for the contact lenses and membrane technology. So because the PDMS have this property of the high permeability, So Professor Chen from France, so he developed this process called microaspiration assisted lithography. So we know that, so when we do the UV lithography, the one potential problem is that if we have a cavity here, there may be air trapped here. If we have air trapped here, the liquid will be difficult to fill in, fully fill in the cavity. So what his group developed, they make this, you have this layer, this is the PDMS. So this layer of the PDMS, it is 20 micrometer here. It is permeable, so you use the pump. There's a pump, so you can pump away the air through the PDMS, pump away. This way, the liquid will be sucked to fill the trench, to fill the cavity. You get a very good imprint. So why the PDMS is so popular? Why it is so popular for research? This is because it's easy and very easy to make the PDMS mold. For instance, you start with the separate with this red color pattern. Then you can pour the PDMS onto this is the prepolymer. Pour onto it. Then you use the hot plate to cure it for a few hours. Then you can peel it off. You peel off the PDMS so you get the mold. So you can see very easy to make. But this red color here, the pattern here can be a photoresist, a silicon, or glass, or other materials. Sometimes you may need to do some salinization process. This one is the same as the most release agent for non-imprinted lithography to give you a low surface energy so that it's easier to peel off, to peel the PDMS off. This prepolymer here is like this. You see, this is that you have 10 parts of this bottle and 1 part of this bottle. You mix them together, you get this prepolymer. You get this prepolymer here. So this bottle here, this one is the PDMS. This one is a curing agent. This makes it cured, cross-linked. So the problem for the PDMS, because it is too soft, with the low Yash modulus. So one problem, the pattern may be collapsed, and it may sag. It may sag. And also, when it is cured, there is a shrinking, 1% shrinkage. This 1% shrinkage is a very big number and make very good alignment difficult. So how to solve the problem of soft? It's too soft. So what we can do, we make it a hard PDMS. To make it a hard PDMS, we can either add some filler material into the PDMS, or we can also use, if we just simply add, we add more curing agent into here, you get more cross-linked, then it also become harder. But then there is the trade-off. So when you have the soft, if we have soft, it's conformal contact and flexible, but it's not good for high resolution. So when you have hard PDMS, you do not have conformal contact, and it is brittle. It's no longer flexible. So there is a trade-off between hard and soft PDMS. So now let's look at fog of the macro lithography using the PDMS. The first one is called macro contact printing. So this idea is simple. So first, you have this master mode. So this master mode can be silicon or glass, or maybe SU8, some photoresist. And then you pour the prepolymer over the PDMS. Then you cure it. Then you cure the PDMS. You peel it off. So you have this mold called stamp. You can see it here. You can see the mold. Then you put the ink solution onto the mold. Then you remove the bulk of the ink and you press it onto the substrate. In this case, the substrate contains the gold and the substrate. So the ink molecule will be transferred to the gold. Then you can use the ink as the mask to etch into the gold. So the question is, what is the good ink molecule? What is the good ink solution? For example, can we use a solvent like IPA? Or maybe use water. So can we use water or IPA solvent isopropyl as the ink? So this will not work because even though you can transfer the solvent onto the substrate, they will dry off. They will vaporize. They will dry off in a short time. So this is not good. The other thing for the ink ink to work as the etching mask, we need the ink to bond. We need the ink to bond to the gold, so that we have very stable ink molecule onto the gold. So what is used for duality is this one, SAM. So what is SAM? So this is the self-assembled monoligand. So here's the definition of the self-assembly. The self-assembly is the spontaneous organization of molecules or objects in the stable, well-defined structures. For example, when we have the gold, so here we have the gold here we have a gold. For the casing of gold, we can use this one, SH group. This is called the cell group. The cell group. So we have this one onto the gold, and the sulfur will bond with the gold, with the hydrogen will be released. As you can see here, they form really well organized. They are all 30 degrees, all point along the same direction. That's why it is called self-assembled monoligand. The thickness is a few nanometers. So this head group here determines the property of this self-assembled monoligand. For example, this X here can be hydrophobic, or it can be this can be hydrophilic, or it can be hydrophobic. This is the self-assembled. This works very well for the gold, and it will also work for the silver. But the problem is that the silver surface is not stable in gold, because in the air, we have lots of sulfur. So when the sulfur comes to the silver will, it will form this. It will form this thing. That's why when you put the silver in the air for a long time, it will become yellow color, because the silver takes the sulfur from the environment. So now let's look at a few examples of this macrocontact printing. In the first example, so the ink is the OTS. OTS is the oxidized trichlorosilane. So we know that this trichlorosilane, so the cell group HH will go to the gold. This trichlorosilane will bond to the silicon oxide that is terminated by the hydroxyl group. So you can use this one as the ink, so you can pattern this OTS on the surface. Then you grow the crystals. So the material is this pantacene, rubrine, and fluorine. So you can see, so the ink here, OTS is mainly this thing. So this OTS is a lot of hydrocarbon. But this one is also a lot of hydrocarbon. This is also hydrocarbon, and this one also hydrocarbon. As a result, those molecules here will go to the ink area. You can see they just go to they got condensed and from the nucleus as the ink area. It formed a single crystal. They grow organic single crystals onto the ink layer. So because the PDMS is soft, so we can also do this on a curved surface. So in this case, we have 1.5 millimeter glass. This is the glass tube. The first, you evaporate titanium and silver. Then you do the macro contact printing. So you have the ink. Go to the titanium and silver. Then you use the ink. Use the red color ink as the etching mask. You activate the silver and titanium that is not covered by the ink. Then you make the electrical contact, and you do the electroplating of silver. When the silver becomes thick enough, you can remove the glass tube by HF. This way, you can have some coil structure. This example is the patterning of the DNA using the macro contact printing. So in this case, the ink is the DNA. So you put a drop of the DNA onto this PDMS stamp, So you have the stamp filled with the DNA. For the substrate, it is functionalized so that it has the positive charges. You have positive charge. So you have amine group. This amine group give you positive charge. So we know that for the DNA, the A is the acid. So A is the acid, right? For example, HCl, this is acid. When you get to the solution, hydrogen is positive ion, chlorine is the negative ion. So chlorine is negative ion. Here the same thing. For the case of the DNA, when you put it into the solution, the hydrogen it releases hydrogen and leave behind a negative charge, like a chlorine negative charge. So this negative charge from the DNA will be attracted to the positive charge of the substrate. This way, you have the DNA pattern onto the substrate. But this is the fluorescent image of the DNA. This is the AFM image of the DNA. And now we look at the second type of the soft lithography, which is called replica molding. Here's the replica molding process. As you can see here, it's very similar to nano-printed lithography. It's very similar to the UV clear nano-printed lithography. So first, what do you have? So first, you have the mold, a PDMS mold. Then you pour the polyurethane, the liquid polyurethane. Then you cure it. You cure the polyurethane. Then you peel it off. So you can copy the mold. You can copy the pattern from the PDMS into the polyurethane. Can you copy a pattern from PDMS to PDMS? So can this polyurethane be a PDMS? So this will work actually, because the mold PDMS is already cured, it's cross-linked, but the liquid PDMS is pre-polymer, so you can copy the PDMS onto another PDMS. So here you can see. So here first you make the chrome mold, then you make the PDMS mold, copy from here. You polyurethane mold, copy from here. So we can copy from PDMS to PDMS, from PDMS to polyurethane. You can also copy from polyurethane back to PDMS. That always work. So this is the original master mold. This is the master mold after 7 copy to the PDMS, 7 times copying to the PDMS. This one is the first polyurethane copy from the first PDMS mold. This is the 6th polyurethane copy from the 5th PDMS mold. You can do copy from one another. So you can see the pattern. They are all 60 nanometers, but pattern height is not very much. It's only 50 nanometers. This is another example using this replica molding. The material is also the polyurethane, the same material. This is also a kind of glue material. So we can play with some tricks. We can play some tricks to make the replica molding. For the first example here, the first you have the photoresist pattern, and you make the pattern, you copy the pattern into the PDMS. Then you squeeze it. You squeeze from the right side, and squeeze from the two sides. It becomes smaller. But while it is squeezed, you pour the polyurethane. Then you cure the polyurethane and peel it off. You can see here, for the pattern in the polyurethane, the page is 0.8 plus 1.6 is 2.4 micrometer. So this the page 2.4 micrometer. But this one at the beginning it is 3.6 micrometer. You get smaller feature size by the squeezing. You can do the same process on a curved surface because the PDMS is soft. In this case, you can even create the curved surface. You can see first you make a structure, PDMS structure like this. Then you pump it. When you pump it, become curved. You copy onto the PDMS. The next example is the micro molding in capillary. As the name indicates, we use capillary force. But what do we do? So first, we seal the PDMS onto the substrate. So this white color PDMS mold seal to the substrate, but this is not permanent. This is not permanent bonding. It's temporary bonding. It can be peeled off later on. Then you put a drop of the liquid prepolymer. So because of the capillary force, the polymer will fill into the capillary. Then it can be cured. So after it is cured, you can peel it off. Here's one example. You get nano features by this process. So here's again the showing the process. So we have the mold, we fill the liquid fill in, then we cure it, we remove the mold. So then the question is how big pattern we can get. So we want large feature set. We want large area patterning. So how large area it can go. That means how fast the liquid will fill into the channels. So obviously the filling speed is given by dz over dt. So here is so the filling is along the z direction here. This is the filling, that's dz over dt. So obviously the driving force. So the driving force is the surface energy. So the capillary force. So this capillary force is the driving force. The surface energy is given by the surface tension is given by gamma cosine theta, right? That's why I have the gamma cosine theta on the top. So the force that prevent this filling is the viscous force, viscosity, this viscous force. And this is because of the friction, the liquid friction with the wall. So we have the friction with the wall of the channels. This is the friction. The effect of the friction is determined by this eta, the viscosity. This is the viscosity of the polymer. So this one should be at the bottom. And also, the deeper you set, the deeper it filled in, the more difficult to fill in because you have more friction. You have more friction with the wall. So that's why you have another term here. You have the Z, this Z term here at the bottom. The deeper you set, more difficult to fill in because you have more friction. You have more friction with the wall. Now this number R, the radius. This for the circular case. So on one hand, we know that the surface tension force is given by from here you can see the bigger the R, the bigger the radius give you higher driving force, higher capillary force. But on the other hand, we have bigger radius. You got bigger radius, you also get more friction by the wall. But in the end, after calculation, the R is on the top. So that's why you get R is on the top. You have this kind of formula. But this one, circular one, is not so easy to derive. Then we have the parallel. If the liquid fill in this, this is like a plane. This is another one. You have this with the parallel. So the liquid flow between two walls. This one actually it can be calculated. The liquid will be something like this. This one you can calculate something similar to this. But for circular one, it's more complicated. But from here you can see that the dz over dt is proportional to 1 over z, right? That means will be something like you get this one. So you can see the deeper you set, the filling will be more and more difficult, take longer and longer time. So here are the examples. This one is the polyurethane. The second one is the polyaniline. So what is special for polyaniline? So this one is the conducting polymer. The third one is the zirconium oxide. You may wonder, this one is oxide, it is a solid. How to fill a solid into the channel? So the process is done by the Solder process. So first we have the liquid. So when we have the liquid, it can fill into the channel. Then we do a high temperature annealing process. During this high temperature annealing process, the material, the gel, will become a solid, zirconium oxide. This is why the polyurethane. This is also polyurethane. And now let's look at another example: microtransfer molding or microtransfer printing. So the idea is also very straightforward. So first, you have the prepolymer. You put under the PDMS mold. Then you use a block of the PDMS to scrape off, to remove the excess prepolymer. You get something like this. Then you put this one onto another substrate, onto this purple color substrate. Then you cure it. So this substrate has higher surface energy, the PDMS has lower surface energy. As a result, in the end, the green color will go to the purple surface. This is why you can see it's very similar to what we have learned before. So we have learned reverse. So this is why you can see it's very similar to the reverse non-printing lithography. And again, you can do 3 times. If you do 3 times, you get this 3 layer of the structures. So here are the examples of the microtransfer molding process. So the first one is the polyurethane. This one is from Norland NOA 73. This is a trade name from the company called Norland. So this one is polyurethane. And this one is the spin-on glass. Spin-on glass. How to do the glass spin-on? This something is also similar to the solder process. So first we have this liquid. You have this liquid. Then you do when it got annealed, it become a solid. It become a glass. So the CDE is the heat cured epoxy. So those material here, they are epoxy. This one is 2-layer pattern. This is also 2-layer pattern. This one is 3-layer pattern. Here is another example of the metal transfer assisted non-lithography transfer printing. In this case, we transfer the pattern from the mold onto the substrate. So first you make the PDMS mold, then you evaporate metal onto the PDMS mold. On the substrate, you have layer of the PMA. Then you heat up to 115 degrees. So this one is higher than the glass transition temperature of the PMA, so that the PMA will become very, very sticky, So when it is sticky, you peel off, the metal will be stick onto the PMA. Then you use the metal as the mask to etch into the PMA. You deposit another metal, you do the lift off, you can get the pattern transfer to the another metal. And this one is after the transfer of the metal mask. And this one is after etching into the PMA. This one is after the lift off. This is the final step here. So the last example is the injection molding. This one is very material technology. I know in Waterloo kitchen area, there are 2 or 3 companies that they do the injection molding. So most of the plastic part we see, like the pen, the toothbrush, the cell phone, most of the part we see is made by the injection molding, because this one is very efficient and low cost. The idea is that you fill in the polymer, then you heat it up. It got melted. Then you do the rotation. It will post into this mold. This is called mold insert at high temperature. Then you cool down so that you make the plastic part. So we will see a short video for this one later on. Now here's the process to work with the PDMS. You do not need to memorize that process, because only if you start to work on the PDMS, you get familiar with it. Otherwise, if you memorize the process, does not help too much if you do not work on it. Roughly something like this here. So this is the PDMS. This is the curing agent. You mix, the ratio is 10 to 1. 10 this one and 1 this one. You mix them well. Then you put it onto the mold. This is like a silicon mold. Then you cure it. This way you get the PDMS pattern. So now let's look at a very short video for the injection molding.